Good afternoon everyone, I'm Mr. Ish. We have already done a video now on the polynomial integration technique, and you know this right here was a template for that. Where n was not equal to -1, the exponent of that base, you could do the simple technique. When n was equal to -1, you know you'd have to bring in the natural log. In this video we're just looking at a variety of direct integration polynomial questions, because at the end of the day polynomial integration tends to be more important than any of the other function types. If you were given this function f of x is equal to 2x minus 3 and you were told to integrate it from an interval 0 to 10, it wouldn't be too hard. You could start with a graph, you don't have to, but when you start with a graph you could visualize it. You know, if x is equal to 0, you'd have a clear y-intercept of -3, and we don't have to be accurate in terms of our graph, but you'd have a upward sloping line because of this +2 and this y-intercept of 0 comma -3. If you're being tasked to find the integral of this function over here from 0 to 10, you know what you're really looking at. From this 0 up to this 10, you're kind of looking at the area bounded by the curve, whether it's below the curve or above the curve. And very well, within the integration procedure, you'd have this built-in effect within that integral to talk about and to deal with this net area that develops. You know, there's a net area because you have a positive a over here, you'll have a negative area over here, and the net area is the difference of the two. And how does that negative aspect of this get accounted for in the integration, or how does it automatically come in? It comes in right here because of this minus sign you're seeing, because when you put this in the integral form, everything will automatically build in and you'll see it. You'll be looking at something like this: from 0 to 10, 2x minus 3 dx. When you separate it out among its integrals, you can do 0, 10, 2x dx. Remember, properties of integral minus. This minus here accounts for the net area effect that we will see. 0 to 10, we can bring this 3 outside and dx. Now you know everything over here is an easy polynomial which will follow this technique. If you were to integrate it, n plus 1 divided by n plus 1, here you have an x to the power of 0. You do n plus 1, n plus 1. The x variable will come in. You would end up having the antiderivative of this to be 2x squared over 2 10 0 minus 3. Here x would come in by virtue of this template, and then from 10 and 0, you know, these 2's cancel out, so you really just have an x squared from a 10 0 limit and 3 10 and 0. How do you solve this? You'll do 10 squared minus 0 squared. This accounts for the first part right over here, and then minus, then you do 3 times 10 minus 0. Remember, it's always the upper limit placed into your antiderivative, subtracted from that the lower limit placed into that same antiderivative, and you get 100 minus 30, and the area of this curve happens to be, or the area affected or bounded by this curve within this interval happens to be the 70 unit squared, however you want to call it, but that's what it would be. Let's look at this question. We have f of x is equal to 3 minus root x, and we would want to look at this again from an interval. Let's just keep it a uniform interval 0 up to 10. How would you go about interpreting this in terms of integration? You'd basically have to do the integration technique that you now know for polynomials for this. What about in terms of a graph? You know, if x is equal to 0, y is equal to 3, so you have a clear y-intercept of 0 comma 3. How about an x-intercept? What value can you put over here to zero it out? If you were to put a 9 over here, 3 minus root of 9 is a 3 minus 3 is a 0, you'd have a good x-intercept over here, and that would be 9 comma 0. So if you're looking at everything from 0 to 10, we're looking at this portion right over here and this portion right over here in terms of the cumulative areas that we're looking at. But again, there's a net change effect because area 1 happens to be positive, area 1, and here area 2 happens to be negative. But you don't have to worry about how you will do all of this in terms of getting a positive outcome or a negative outcome, because the integral will automatically account for that when you set it up. How will you set it up? You'll do like this. From 0 to 10, you have 3 minus root x dx. You can rewrite it as 3 0 to 10 dx. You know, here you have x to the power of 0 minus, from 0 to 10 you have root x, which is x to the 1 over 2 dx. Remember, always write things in friendly formats because they help you to see things in this way, and then you integrate them. When you do the integration of this, or the antiderivative determination, remember, all of these direct integration questions are actually indirect integration, except to the point where you put the integral limits. Until then, they're still indirect. From here, you just generate an x, and you know that now. X to the power 0, n plus 1 divided by n plus 1. Here you'll have x to the 3 over 2 over 3 over 2, 10 and a 0. Here you'll get 3 In this x you put 10 and you put 0, you do the difference of these two. Flip this fraction, you have 2 over 3, and then you have 10 to the power of 3 over 2 minus 0 to the power of 3 over 2, and we can get a good value over here. We'll do this in terms of a decimal, we'll do this and we'll get the final answer, because this right is arithmetic only. We'll publish the answer here. When I do all of this, I get this as my answer, 8.918, and that represents the area below and above the respective portion of this curve from 0 to 10. Let's take a look at this interesting polynomial, 2x cubed minus x squared. If you were to put 0 in terms of x, you would get y value of 0. So you know this curve will go to the origin. For sure it goes to the origin. If you were to put a value of 0.5 or half in terms of x, you'd get an x-intercept over here in terms of 1 over 2. So an x-intercept over here is 1 over 2 comma 0. You could end up seeing that the graph would look something like 0 comma 0 is a good point on this curve, and half comma 0 is a good point on this curve. We're looking again from 0 to 10. We're looking at from 0 all the way up to wherever 10 might end up. This portion right here and all of this area which would show up on the curve is what we would examine, and you know there would be a net area effect over here, because you have this little small area right here which would be minus, and you have this very large area which would be positive. But again, the integral setup will take care of all of that. You'd be looking at 2x cubed dx minus x squared dx. You know you're looking from 10 to 0 in both instances, and these integrals are very easy. You have 2x to the power of 4 over 4 using this technique right here from 10 and 0. Here you have x cubed over 3, again from 10 and 0. This becomes x to the power of 4 over 2 from 10 and 0, minus stays the same, x cubed, 10 and 0, and now we have to do nothing more than publish the answer. 10 to the power of 4 divided by 2 minus 10 to the power of 3 divided by 3. We can just put a good decimal answer over here. In all these instances, putting the zeros into these antiderivatives is meaningless. You just can get away just putting the upper limit, because the 0 will have no effect. And your answer would be 4,666.667, and that would be the area of this curve, the area bounded by the curve. And let's look at this one. We'll be looking at this one more, and that'll be it for this video, because we just are reaffirming the technique for polynomial integration we already know, but with the perspective of this area below the curve. This seemingly easy question is quite tricky. It's not tricky in terms of arriving at the answer, it's tricky only in terms of interpreting the answer that you will get. If you do 1 over x, you know in terms of a graph, it looks something like this. It has a domain over here from minus infinity up to 0, but then it splits and then continues from the other side, 0 up to infinity. When x is approaching 0 from the left, your function goes and approaches minus infinity, and you see this curve down over here. When x is approaching 0 from the right, your function, see when you're approaching 0 from the right, your function approaches positive infinity, and you can see this part over here. Our problem arises when we're trying to find the area of 1 over x from 0 to 10, because, well, up to 10 here it's all nice and good up to here, but the minute you start coming over here where you know your curve hits this vertical asymptote, it'll never reach it, then how will you end up determining the area? And that's a problem which will arise, and you would not end up having an area determination for this question, but we can work it out and see why mathematically that's the case. If you're looking at the integral of this from 0 to 10, you know you have 1 over x dx, which is the same thing as looking at 0 to 10, x to the minus 1 dx. You know here in this case you have to use this rule in which you bring in the natural log. That's fine. When you do the antiderivative of this, you get natural log x, but from 10 to 0. If you were to do this in terms of this, the problem arises with this lower limit. When you're doing natural log, you can do a natural log of 10, then you're doing natural log of 0, and that's our problem. This is easily calculated on your calculator, but this right here, you can't determine a value for, because any natural log curve, as you know, going from 1, 0 in terms of its x-intercept, the natural log curve approaches 0 going here into the direction of minus infinity, which you can think of as positive infinity. And this part over here, if you do your natural log of 0 on your calculator, you get an error. You get an error which shows up, so you can't do it. You can very well do a natural log 10, but you cannot do this part. So in essence, what you're really looking at is natural log 10 minus some sort of an infinity value, and this ends up being a problem in terms of area determination, so you can't do it. The only way you can do this type of question is if you clearly define the limit but not 0. If you were to change this 0 up to a 1, then you could easily do it, because now in this instance all of these zeros will get replaced by 1, and you know 1 is very well within the domain of this terms of right over here. 1 is very well falling within the domain of this hyperbola, this curve we have, and it very well falls within the domain of a natural log. So here then you end up putting 1, and then you end up putting 1 over here. You get a natural log of 1 as a 0. In this instance you can easily solve natural log of 1, and here your area is just equal to natural log of 10, and you know you can calculate that because this part right over here becomes a 0. So your area for this curve now going from 1 to 10, is just equal to natural log of 10, and that is easily determined. 2.302585093 would be your answer. So we will end our video with this last question. We have f of x equals x minus 1 over x from 1 to 10. Graphing it, first thing, convert it into a rational function, common denominator, and then you'll have x squared minus 1. You know you have to think back to the asymptotes. You have n and you have m. Remember that, how you calculate the asymptotes. The highest order exponent in the numerator, 2. In the denominator you have a 1. In terms of vertical asymptote, you're looking at the 0 of the denominator. X is equal to 0 is a vertical asymptote. Horizontal asymptote, in this case n is larger than m, so there is no horizontal asymptote, but oblique asymptote, n is equal to m plus 1, so you know you will have an oblique asymptote by means of polynomial long division. X squared minus 1 divided by x. X goes in here, x times, you have x squared. You minus them and you just end up having a minus 1. What do you get over here? You get x plus minus 1 over x. That ends up being your long division result, but you only look at this, and y equals x is your oblique asymptote. If you look at this function over here, you can't put a 0 in the denominator in terms of an x value, so you know the origin is by no means involved. You have oblique asymptote of y equals x, you have vertical asymptote, your y-axis, and you know pretty much your function is going to go and traverse the y equals x and the vertical line, the y-axis. It's going to look something like this. And on this side you'll have something which will come right over here. But you can easily define this point right over here. If x is equal to 1 in all of these instances, x minus 1 over x, if you make x equals 1, you get 1 minus 1 over 1, you'll get 0. So when x is equal to 1, the y value is 0. So you know 1 comma 0 is a good x-intercept. In terms of domain, what are we looking at domain over here? The domain, you go from minus infinity up to 0, and then from 0 you go up to infinity. You have this little break in between. So now we know what we're looking at here in terms of the graph. What are we looking at here in terms of the area under the graph for our integral question from 1 to 10? You know you're looking from here 1 all the way up to this 10. So you're looking at this region over here, and that's what we have to examine in terms of integral. So this by no means is a hard question. You know you're looking at here from 1 to 10, you're looking at x minus 1 over x dx. You can separate it out around the minus. You're looking at 10, 1, x dx minus 1 over x dx. Integral of this using that rule right there, n plus 1 divided by n plus 1, you'll have x squared over 2 going from 10 to 1. This can be viewed as x to the minus 1. And you know when you have that, you have to bring in the natural log. So you can have natural log x come in over here from 10 to 1. What are you looking at here in terms of an answer? You have 10 coming in here, you have 1 coming in here. 10 square minus 1 square, it's always the difference of the two. You have 99 over 2. Here you have natural log 10 minus natural log 1, both of which are easily solvable. This is a 0. You have 99 divided by 2 minus natural log 10. You can give a good calculator answer. Let's put the answer here. The area below the curve for this designated region is 47.197. The outcome of this integral procedure over here. That's pretty much all I wanted to show you for this video. Keep in mind, these type of questions are not hard. Once you know the template scheme, it's not hard. At the end of the day, everything is always relating to areas between curves or areas under curves or above curves for that matter, because all of these represent models in real life having some practical useful application. All models can be graphed, and based on what the units are along the x and the y-axis, the areas or the graphs represent some meaningful result. I hope you enjoyed this video. Thank you for watching. Have a nice day.